In this video we discuss quantitative aspects of precipitation reactions. In particular, we pay attention to how this is connected to equilibrium applications. Right, so let's take a general precipitation reaction, for example, the reaction of sodium carbonate with calcium chloride. Okay, so here you have calcium chloride reacting with sodium carbonate. Right, and this generates a precipitate, which is calcium carbonate, and then 2 moles of sodium chloride, which is a soluble salt. Right, so this is what we call the molecular equation of the precipitation reaction. Now we can write this in terms of the complete Ionic equation, which simply shows the species that are dissociated as ions and those that are insoluble. Right, so this would turn into the following: calcium 2 plus, all of this is aqueous, plus 2 Cl minus, aqueous, plus 2 sodium plus, in aqueous phase, plus carbonate 2 minus in aqueous phase, to give calcium carbonate, which is soluble, and then 2 sodium ions aqueous phase plus 2 chloride ions in the aqueous phase. Again, that is the molecular equation, that is the complete Ionic equation. And then to actually understand what really is going on, then what you do is you take a look at the complete Ionic equation and see what of the species are changing from reagents to products. Right, so we can see that calcium and carbonate are different in reagent and products, but chloride and sodium are exactly the same in reagents and products. So these are spectator ions, and they're not doing really anything in the reaction. So you can completely eliminate them to write what we call the net Ionic equation. Right, so the net Ionic equation will be calcium 2 plus in aqueous phase plus carbonate 2 minus in aqueous phase, precipitate to generate calcium carbonate, which is a solid. Great. Now what we could do is write the equilibrium constant for this process. Right? We would say the equilibrium constant for that process would be the activity of calcium carbonate over the activity of calcium 2 plus times the activity of calcium of carbonate 2 minus. But of course we know that the activity of a solid happens to be 1 by convention. And then the activities here, we can map them into terms of concentrations. Calcium 2 plus and then carbonate 2 minus. Generally, you just divide them by the reference state, but for convenience, we just forget or omit that division. What is obvious is that the units of the equilibrium constant should be 0, no units. Right. Something important about this equilibrium constant is that this is exactly the inverse of the solubility product. And that makes perfect sense, because notice that the precipitation reaction is exactly the opposite, the inverse of the solubility equation. Right? So that makes perfect sense. And in principle, you can sort of quantify how these solubility, or what these precipitation reactions do using this type of equilibrium constants. But the questions that we're interested now would be as follows. Suppose that we mix calcium ions and carbonate ions in some concentrations coming from 2 different solutions, right? So in this particular case, we have calcium coming from calcium chloride, carbonate coming from sodium carbonate, and they will have some volumes and different concentrations. The question is whether we can predict whether by mixing those 2 solutions of calcium ions on one side and carbonate ions on the other side, we will get the precipitate calcium carbonate. Right? So there's an easy way to answer that question, and that is to simply examine what we call the ionic product. Okay, so the ionic product is going to be the concentration of calcium 2 plus times the concentration of carbonate 2 minus. Okay, so it's the concentration of the ions, but these are not equilibrium concentrations. Those are the instantaneous concentrations that you get when you mix those 2 solutions with whatever volumes and whatever molar concentrations you have. Okay, that's something that is important. These are not the equilibrium concentrations necessarily. This can be any concentrations at the start of your process. Right. So if the solubility, the ionic product is larger than the solubility product, then you get a precipitation, that a precipitate forms, right? So that would be positive. When Q is larger than KSP, then the precipitate will happen. Okay, but if Q is lower than KSP, then you actually don't have enough ions to form the precipitate, and a precipitate will not form. All right, so let's actually try to illustrate then this comparison between the ionic product Q and the solubility product KSP by doing a couple of numerical examples just to illustrate this particular point. All right, so in our examples, we're not going to be using calcium carbonate. Instead, we're going to be using a slightly different solution. All right, so let's do here barium chloride. Here we're going to be mixing 1.00 mils of barium chloride. And the concentration of this barium chloride is 0.010 molar. And we're going to be mixing that with 1.00 mils of sodium fluoride with the same concentration. And the question that you have to ask is whether a precipitate forms when you actually mix these two solutions. All right, so let's try to see first what type of compounds you can get out of that. All right, so barium chloride is soluble, sodium fluoride is soluble, so the expectation is that you might be able to find sodium chloride, but we know that sodium chloride is soluble, and then the other possible compound would be barium fluoride. And it turns out that barium fluoride is not soluble. Right? Barium fluoride is it's an insoluble salt, and the solubility product of that barium fluoride happens to be equal to 2.4 10 to the minus 5. Okay, so this will be the question. Does any barium fluoride form when you mix 1 mil of 100th molar barium chloride with 1 mil of 100th molar sodium fluoride? Okay, so let's try to do the calculations. Again, as always, the way that we're going to proceed here is to calculate what is called the solubility, the ionic product. Okay, so the ionic product for this case will be simply the concentration of barium 2 plus times the concentration of fluoride minus squared. Okay, that will be your Q. Alright, so then let's try to figure out here what the concentrations of each one of these ions are. An important detail here is that you're actually diluting the concentrations of those ions. Notice that you have 1 milliliter of barium chloride with 1 milliliter of sodium fluoride. When you mix them, those ions are going to be together in solution, but now the volume is twice what you had, right? So there is an effective dilution that you need to take into account before you can calculate those concentrations after the mixing has taken place, right? So the way to do this is by simply doing a dilution, where you have the volume multiplied by the molarity of the first solution times the volume is equal to the volume times the molarity of the second solution. Okay, so let's try to see how this would work for either one of them. We can do barium or fluoride. In this case, they're actually the same because the volumes and the molar concentrations are exactly the same. Right, so the initial volume is 1 milliliter, so that is 1.0010 to the minus 3 liters multiplied by the initial concentration, which is 0.010 molar. And this is going to be equal to the final volume, which will be 2 mils, okay, so 2.00 10 to the minus 3 liters multiplied by the second concentration, which is what you need. Okay, and that M2, which is the same thing as the concentration of barium 2 plus, and it's the same thing as the concentration of fluoride minus, just from the data in the problem, then that happens to be just half of what you initially had. Right, so this is going to be 0.0050 molar. Okay, so now we can come back here to the ionic product and calculate what the Q is, and then compare it to the solubility product and see if it's larger or smaller. Okay, so the way that you would do this is simply plug in here those values, 0.0050 multiplied by 0.050 squared. Okay, and that number is 1.2 10 to the minus 7. Right, so for this particular case, because the ionic product Q is lower than the solubility product, then what we'll have is that a precipitate does not form. You actually need more ions in order to be able to see barium fluoride precipitating out of solution. Okay, so this is kind of the application of this ionic product. Let's then try to do a final example in which the concentrations are sufficiently large that the precipitate will form. Okay, so the problem is going to be exactly the same, but instead of the concentrations being 100th molar, we're going to have 0.060 molar for each. Okay, so we will repeat the problem much as before. The only difference is that now that will be 0.06, right? And that means that here you will have half of that. So this is going to be equal to 0.030 molar. Okay, you come to this expression right here, and then those concentrations will be 0.030, 0.030, and then when you carry out that calculation, this happens to be 2.7, 10 to the minus 5. Okay, so now that you have more concentrated solutions of the initial ions, when you calculate the ionic product, you get a number that is larger, slightly larger than the solubility product of the salt, and what that will mean is that the precipitate will form. Alright, so in this video we have taken a look at how to treat precipitation reactions from the point of view of equilibrium constants. What we have seen is that there is a metric to predict whether a precipitate will form by mixing two solutions of the ions that are formed in the salt. If that ionic product is larger than the solubility product, then a precipitate will form. If the ionic product is lower than the solubility product, then the precipitate will not form.